Thank you very much again. I'm Hyeun Jun Moon from Gangwon University. I'm very honored to be here, and I'd like to thank to Professor Kim and Chairman. Today, I'm going to talk a little bit about BAMS technology. Usually, I gave a presentation regarding building simulation technology for moisture transportation or mold growth. But today I changed a little bit topics related to building energy systems. So I want to talk about how building simulation technology can be used for building energy management systems. I think this is very good in line with Dr. Maria Todorovic. She mentioned about building performance simulation and co-simulation for better building energy management systems, especially connected to smart grid. I think we can a little bit talk about real-time simulation and how can this technology can be used for actual building systems. Let's take a look at a little bit of background. First, all of you know that today Korean government issued that we may have a short of power, electric power today. And they also issued same warning yesterday, the day before yesterday. So we expect that over the summer we may have big problems in energy in Korea. Let's a little bit take it back 2 years ago. In 2011, September, Seoul had experienced blackout. Maybe you can remember. Which means we have excessive power demand over power supply. The more serious problem is after that day, the next day, Korean consumed more energy than the blackout day, which also means we need to develop some kind of new demand control strategies and new technologies. Maybe we can see that we need to develop something, but we still don't know what it exactly should be. In this room, I feel that the temperature a little bit colder than I expected. Maybe you may have the same thought. And we also can think about that. We can manage better building energy management for this building. You may think that. I also think the same way, so that how can we save more energies in actual buildings? That kind of topics is one of the hot research topic in building energy sector. Let's take a look at a little bit of building energy consumption. As you know, buildings consume about 40% of total energy. Within this 40% of energy, residential building consumes 20%, 22%, and commercial building consumes 18%. Most of energy consumed for heating and cooling. Same for commercial building. And the lighting is one of the big issues. So if we can save some energy for this part of building energy, we may be successful to overcome energy crisis in this year or next year. So many people think about BAMS maybe the one of the technology we can attack. So using this BAMS system, we can save more energies, and then using this BAMS technology, we may also reduce greenhouse gases. And if we take a look at the market share, we can expect globally annual average 6% of increase in BAMS system. But in this slide, I'm talking about current BAMS system, not the new technology with BAMS. which is called smart BAMs. When we talk about BAMs, there are many limitations at this time. First of all, most of systems are focused on monitoring functions only, which is based on BAS system, building automation system. So we can collect some information, but we don't know how to use that information for better control for building energy. So we try to think about and come up with a new approach for better building energy management systems. The other issue is lack of control algorithms. So based on the building energy data from BAMs, we have to use this information for actual building control. Maybe we can control temperature, or maybe we can control ventilation systems, or maybe we can control lighting systems. But to do that, we have to connect this information with actual hardware control systems. Also, we are lack of optimal control algorithms. So that the research topic in this paper is about the control algorithms for BAMs and simulation technologies. Let's summarize the objective of this paper. It is to develop control algorithms and smart BAMs for higher energy savings while maintaining appropriate occupant comfort and indoor quality. To accomplish this objective, we adopt a couple of new methods. First of all, we use real-time simulation-based control approach. And the other one is real-time simulation, which is software, and BAM system, which is hardware. So how can we integrate this software and hardware? That is one of the issues in this paper. And after that, we demonstrate the feasibility of this integrated system in real building. And then we adopt a model-based control for building operation. I know we are short of time, so I will keep up with the presentation. First we can think of how can we use building data in design stage and operation stage. I'm talking about existing building, which is actual building, but the building information was from design stage actually. So how can we integrate and enhance this interoperability? If we can do that, we can save a lot of time and energy to make a building simulation model for existing building. So let's take a look at this figure. So we start from design stage. In the design stage, we can make a model for building performance simulation. And we can calculate the building load, and we finish the design stage. But if we can use this information for operational stage, the information can be transferred to a new or enhanced building reference model. So with this model and with existing building, we can populate new information to this model. Then we can learn real-time simulation, and then we can use model-based control for this building. In other way, I can explain it from real building. We can monitor new information or existing building information through smart meter to virtual building. So they're using this virtual building like as an energy plus model. We can simulate and test with optimal control algorithms, and then the result can be transferred to BAMs, and through control devices we can operate in a new way for existing building. To accomplish this system, we have to integrate a couple of hardware and software. We use BC VTB which is building controls virtual testbed. This middleware was developed by LBNL. So using this middleware, as you can see in this figure, we can connect Energy Plus, Modelica, or Simulink, which are softwares, to BankNet. So that if you have a hardware which you can control with BankNet, you can actually connect simulation program and hardware. You can also use other programs like as a window or ESPR, something like that. So we use this technology, and we developed a real-time simulation-based BAMs. Let me introduce this figure. We can start from here. From BAM system in actual building, we can sense a couple of energy data through BankNet gateway. Then we can transport this information to simulation actor until to Energy Plus. So from this simulation function, we can go the other way. So through actor, the result transport to actually controlled device. We can also use database systems. Let me introduce two case studies with this integrated system. First one is about a boiler system which use nighttime electric boilers. This building doesn't look like a residential building, but the function is a residential building. So with this building, we have two boiler systems. So we installed the BCVTV server and the simulation programs. So we collected a couple of data from actual building, and then we run real-time simulation with outdoor temperature and relative humidity and boiler operation status. So that the results are for floor heating rates for actual building, so that we can compare the simulation result and actual result. So I know we have short of time, so that I will skip this one. So while conducting this research, we can compare simulation result and actual data, so that we can go through with FDD, fault detection, and continuous commissioning as well. So at the end of the comparison stage, we have a very good agreement between simulation result and actual data. So that actually we run with a new control algorithm which is based on calculated heating load. So we can compare with the current algorithm, which is based on return temperature based control and new simulation based control. So that we can, as you can see, the new control algorithm can save more energy. But in terms of temperature, we don't need to compensate the temperature or summer comfort, which is good. The next one is about the ventilation system. This one shows ERV system, which is connected to BCVTV server. And this figure shows BCVTV program. And this one shows a control device which is connected to ventilation systems. So in this case, we learn a couple of ventilation strategies, which is about 0.3, 0.5, 0.7 air change rate for a specific building. And we compare this current control approach with the simulation-based control, which means if we have a 1000 ppm of CO2 in a room, we learn ventilation system. And we developed this, realized this simulation system with EMS in Energy Plus. So that this shows the result of the distribution of CO2. So the green line shows the result from simulation-based control, which shows very good maintenance of indoor CO2 levels. And this one shows the in green lines you can see the difference, right? So which is when we introduce ventilation, we have we experience increased cooling load, but when we learn simulation-based control, we don't have much increase of cooling load. So this is good for our system. Okay, conclusions. So we established the real-time simulation-based BAMS system. We successfully integrate Energy Plus and actual BAMS system through BCVTV. So through using case studies, we demonstrated FDD and continuous commissioning through comparison between real-time monitoring and simulation results. We can also confirm the simulation-based control for energy efficient performance while maintaining an appropriate occupancy comfort and IAQ. We also proved the energy saving potential in this integrated system. Thank you very much.